Good morning, everyone. This is Mr. Couple. I'm here today with my IBSL Year 2 students, and we're going to be talking about the parallax method of measuring the distance to nearby stars. Before I go into showing you guys how to actually do the parallax method, I wanted to first show you just some distances that you might be more familiar with, because going out to like really far distances to far, far away stars is kind of a little bit of a big jump. So let's first start talking about the distance to just planets. So first I want to talk about, well, how far away is the Earth from the sun? Do any of you guys know?
One.
One. You cut off.
For some reason, I remember like 93 million miles.
It is 93 million miles. So it's 93 million miles. There's a song that has it in it.
That's where I remember it from, I think.
They Might be giants. Yeah, it's like the sun is a massive incandescent gas, a gigantic nuclear furnace. Have you heard that one?
Oh yeah, that was I grew up with.
There you go. It's 1.5 times 10^11 meters, and we call this, in simple terms, we call it 1 AU, where AU stands for astronomical unit. Maybe you guys have heard of that? Yes, no?
Yeah.
All right, so how far away is Jupiter from the sun? So we're going to go all the way out to Jupiter. Nope, that's Saturn. Take a guess, guys. How many AU?
Like 2.
2. It's 5. So, yep, if the Earth is here-ish, then you can see going out to there is about 5. Okay, let's go out to Neptune. Neptune is the furthest planet from the sun that we know of. There's speculation that there might be a ninth planet, but they're still looking for it. So how far away do you think it is to Neptune? So there's Jupiter. Jupiter's right there. So how far out to Neptune? No one's going to say anything?
14.
It's 30. Wow. Okay, if you continue on past Neptune, you get to what are called the trans-Neptunian objects, or in the Kuiper belt. That's where you find most of the dwarf planets, like Pluto and what else is out there? Haumea. I don't remember the names of the dwarf planets. If you go out even further than that, past the Kuiper Belt, there's this theorized place called the Oort Cloud, and we think that there's a bunch of little tiny frozen bodies out there, like what will eventually become comets and things like that. There's also, speculated that there might be this ninth planet out there, but this thing is called the Oort Cloud, and it's like the furthest reaches of like what you would call the solar system. And so the Oort Cloud begins about 2,000 AU away from the sun. If we keep going out even further, here's an interesting picture I got off Wikipedia. So there's the edge of the Oort cloud, and remember the Oort cloud starts right there where it starts, like this starting point here. Whoa, the starting point here, that's where 2,000 AU is. So if you keep going past the Oort cloud, further and further and further, you reach the Alpha Centauri system, which is the nearest star to the Earth. And so how many AU is it to Alpha Centauri? So it turns out that it's 280,000 AU. So we start to have a problem with using AUs. Like AUs are really good for as long as you're within the, inner planets or the solar system. But once you try to go out to further stars, the astronomical unit is just way too small. We need bigger units. Do you guys know what those bigger units are? Like, are there any that you've ever heard of before?
Light years?
Yeah, light years. So Alpha Centauri is 4.3 light years, so it's LY. And then there's another unit that's also mentioned. It's called the Parsec. Have you guys ever heard that? All right, calculate the length in meters of 1 light year. Now we're going to do that later. Okay, so that's where I'm going to stop talking about distances. So the parsec is the one that we're going to really concern ourselves with, and that's what this entire lesson is about. It's about the parsec. Ooh, just got really bright. Okay, so I'm going to start off by telling you guys about the parallax method. We're going to try to derive an equation that will tell us how far away a star is. My webcam's in the way. I'm going to move it down here. Do I even need it? Maybe I'll just delete it. I'm going to delete it. Bye. Okay, so I'm going to start by showing you guys this picture. This is illustration of the parallax. So this is how you would figure out the parallax angle. So the way it works is like when you're looking at the star. So here's the star that we're looking at. At one point during the year, so if we're at this location in the Earth's orbit, the star will appear to be at this location. But then when the Earth orbits around the sun and reaches this other position, that star will have appeared to move. And the reason is because it's closer to us than these distant background stars. So these distant background stars are so far away that they don't appear to move. So like I want you guys to like take your thumb and like hold it out at the end of your hand, and then like you can just open one eye and close the other eye, and like your thumb will it'll appear to move back and forth. And so that's the whole idea of parallax. Is like based on when we're looking at the star at different points in our orbit, it will appear to be in a different location. So this is called the parallax method, and it only works for nearby stars. So what you do is you use a telescope and you can measure that how far the shift was. So like how far did that planet shift? And based on that, you can determine this thing here, which is called the parallax angle. And we call that angle P. Now, because of geometry, we can actually work out what the distance to this planet is. So from the sun, not planet, star, we can find out the distance to this star from the sun. And we're going to call that lowercase d. And the reason why is because if we've measured that angle and we know how far we are between these two measurements, see that's from the Earth to the sun, right? That's the radius of this circle where we're at two ends of the circle making this observation. That's just the radius of the Earth's orbit. And so we can create an equation that tells us what d is. So if we solve for d, actually what we're going to do is we're going to use that angle P, and you're going to take the tan of that angle. Because what happens if I take the tan of angle P? So what are we going to get? You guys still there?
D over R.
So tan is opposite over
Oh,
adjacent.
R
So
over
from
D.
P, yep, so it's going to be R over D. But here's the thing, we already know what R is. Like that's what I was just talking to you guys about. How far away is it from the sun and the Earth? That's just 1 AU. And so we know that this is going to be, if we solve this for D, so D is going to equal 1 AU divided by the tan of that parallax angle. And that'll give us the distance to the star. So you just take a picture of a star at 2 different times during a year, and you can measure the parallax angle from that, and then that will let you know how far away the star is. The limitation, though, is it only works if the star is close, that there's a fixed background behind the star. All stars are extremely far from the sun. The closest star, Alpha Centauri A, is 4.3 light years from the sun. Qualitatively describe the size of the parallax angle to a star. So what are we going to find? Think about this. Like that distance d is way bigger than r. So r is 1. So d is always way bigger than r. So you'll remember back over here, for the nearest star, it's going to be 1 divided by 280,000. And that's for the nearest star. So when we go to plug in here, you're going to have 1 divided by 280,000 for the distance when you compare R and D. So what does that tell us about that angle? That D is 280,000 times bigger than R. Then what will happen when you go to find that ratio of R over D? The angle is going to be what? What size?
It's much smaller.
Yeah, so P is going to be nearly 0. It's a very small. It's a very small angle. So now what we can do is we can use what's called the small angle approximation. So there's this thing in physics where when the angle is really small, you can say that, well, it's usually sine of the angle, but it also works for tan. You can say that tan of an angle that's really small is approximately just equal to the angle. If P is approximately 0, then the tangent of P will be about equal to P. So we can use that small angle approximation, that's what that's called, to rewrite our equation up here. Is we could write it as D equals to 1 AU divided by P. So we've just gotten rid of the tan, which is great because tan is annoying to try to calculate. Okay, we're not done yet, so let's define this new unit called the parsec. And the reason we're going to define the parsec is because it's much easier to use this distance in this equation. So this unit of measure was literally invented because of this equation. 1 parsec is equal to the distance from the sun to a star, which has a parallax angle of 1 arcsecond, hence the name parallax second. So parallax second is where you get the word parsec, so it's parallax second. You just take the 2 parallel second, parsec. It's the distance from the sun to a star where their parallax angle is 1 arcsecond. And so now every time I read this definition to students for the first time, like, what the heck is an arcsecond? What's an arcsecond? So I have this picture I'm going to show you guys. See if it works. Where is it? Here it is. And it's not displaying it correctly. Oh, it's so annoying. How do I make this have a white background? Oh, I know. I have to use the Edge browser. Let's see if I can. Where is my Edge browser? The Edge browser displays this correctly. Come on, keyboard back on. Edge. Okay. Okay, let's see. Bring this over here. Oh my god, it's still not displaying it. I'm so upset. Never mind. I guess I'm not gonna be able to show you guys this image. Wait, I have one last idea. I can load it in Word. Oh, this is what happens. Don't upload images with transparent backgrounds. Okay, here we go. Okay, I finally got it to work. Okay, so an arc second is if you take an arc minute and break it into 60 pieces. Well, what's an arc minute? Well, an arc minute is if you take a degree and break it into 60 sections. So when you take a 1 degree angle on a circle and you break it into 60 sections, one of those is called an arc minute. And if you take one of those and then break it into 60 sections, that's called an arc second. Does that make sense, guys? Like, let me know what questions you have about this. Have you heard of those before? How about that? Have you guys ever heard of the arc second and the arc minute?
No.
It's weird, right? Because they're so small. But I mean, it makes sense, right? Because we just said that the angle that the star, you know, the parallax angle is going to be crazy small. And so you need to divide a degree into way smaller sections in order to measure it. It's going to be such a small angle. Okay, so the symbols we use is if you want to do an arc minute, you just put a little tick. And if you want to do arc seconds, you put 2 ticks. You kind of like what we do like with inches and feet, right? So that's kind of the way that astronomers will do it. So if you ever see it say like an angle of 2, double tick, that means it's 2 arc seconds. Okay, back here. Determine the size of 1 arc second in radians. And so we have to do it in radians. It's kind of weird. But the reason you do it in radians is because remember back up here, it was tan of P. And so the parallax angle is always going to be measured in radians. So what we're going to do is we're going to take the arc second and we're going to measure it in radians. Okay, let's try to figure this out. So 1 arc second. So 1 arc second. I'll just write it like this. 1 arc second is equal to 1 over 60 times 1 over 60 times 1 degree. So I just took, it's a 60th of a degree, but it's a 60th of a 60th of a degree, right? Because it's a second. If we just wanted the minute, so this one here, that gives us the arc minute. So we're taking 1/60th of 1/60th of 1 degree. And so that's what an arc second is. So arc second is going to be equal to 1 degree divided by 3600. But we didn't want it in degrees, we wanted it in radians, so we're going to need to convert the radians. Who remembers how to convert the radians?
Multiply by pi over 180.
Yep, pi over 180. And then that's going to give us the angle in radians. Now, here's a thing to remember. A radian is actually not a unit. It's a unitless quantity, but we just put radians there to remind us that there is no unit here because you can see that these degrees have canceled out, so there's no unit. Okay, let's do the calculation. So 1 arc second is equal to, so now we just have to take pi divided by 180. I'm going to grab my calculator. Wait, I should be able to just display the calculator on the screen here. Oh my gosh, I have too many windows open, guys. Okay, here we go. And then I'll bring my webcam back up again. Oh, I'm like way off screen. Okay, there we go. Okay, what am I doing? Okay, here we go. So I'm gonna take pi. What the heck? Come on, where's pi? Oh, there it is. Pi divided by 180. And I'm going to take that, I'm going to divide it by 60 times 60. Let's get 4.848 times 10 to the negative 6. I'll just write all of that. So 4.848, 4.848 times 10 to the negative 6. And that's going to be radians. So that's an arcsecond. It's like 5 millionths of a radian. It's a really, really small angle, but that's typically what you're going to see when you go to measure stars. It's going to be this really, really small, small, small angle. Okay, so now let's determine the distance of a parsec. So if we want to find a parsec, it's the distance from the sun to a star which has a parallax angle of 1 arcsecond. So we can use our equation which says that d equals to 1 AU over P. But what we're going to do here is we're going to use the distance of the Earth's orbit, 1.496 times 10 to the 11 meters, divided by P, which is what we just found over here. So if the angle P is going to be 1 arcsecond. So we're going to divide by 4.84 times 10 to the negative 6. 4.84, what was it? 848 times 10 to the negative 6. And then that's a unitless quantity, so I won't put a unit on there. Okay, so I'm just going to take the distance from 1 AU, 1.496 times 10 to the 11, divided by that arcsecond in radians that we just found, and then I get this, 3.0857. So this is the parsec. So distance, so 1 parsec, 1 PC. PC is the abbreviation for parsec. So 1 PC is equal to 3. Let's round it off, 3.0. I'll put 3.086 times 10 to the 16 meters. Generally, the way you'll find it, like if you looked it up in the IB data booklet, they'd put 3.09, but I want that extra digit of precision for something that we're going to do on the back of this page. How am I doing on time? Like less than 15 minutes. Okay. So that's 1 parsec. So it's a ridiculously large number of meters, but that's good because we wanted to come up with a really large unit that we can use to measure the distances to nearby stars. Part C, rewrite the parallax equation in terms of the parsec. Okay, so here's the trick. This is really cool. So that equation that we had, which said that distance equals 1 over p, this equation works if you put in the angle here in arcseconds. So if you put an angle in arcseconds in there, it will give you out a distance in parsecs. And so that's all you have to do is just take the reciprocal of the arcsecond angle measurement, and then you'll get the distance in parsecs. And that arcsecond angle is always going to be given to you in radians, as we'll see when we start to solve problems. Question D, outline the limitations of using the parallax method to measure the distance to a star. So what are the limitations of this method, guys? Like where does it go wrong? Or where does it work?
It requires us to know the angle.
Yeah, so we have to be able to measure it, right? So it requires the measurement. And tell me about that angle.
Of an infinitesimally small angle.
Yeah, so it requires a measurement of an incredibly small angle. And so what's that going to do? It means that we can only use this on stars that are located where?
Within our galaxy.
Even less than that.
Within our system.
No, because there aren't stars in our system. But this only works on nearby stars. So it's not going to work beyond, like 1,000 light years. Like it's not going to let you go very far. And it's just because with a telescope it won't. And also the problem is that like if you're looking at a star through the atmosphere is going to distort and kind of bend and like ripple the light, and so you won't actually be able to really measure the parsec angle very well because you're going to have all these distortions through the atmosphere. Now, if you throw up a space telescope, then you can get really good measurements. So that's the last question. This is the question I'm going to have you guys do for the check your understand or demonstrate your understanding. But this is the Gaia space telescope. So if you put a telescope up in space, it can actually, you don't have to deal with those atmospheric distortions anymore. And now all you have to do is worry about what's your instrument sensitivity. So the Gaia space telescope can measure down to the micro arcseconds. That's pretty impressive. So, when we say nearby, that's relative to the sensitivity of your instruments. So realize that like if you're using a telescope on the surface of the Earth, you're not going to be able to measure stars very far away. But if you're using a space telescope with extremely high-tech sensitive equipment that can measure micro arcseconds, well, then you can measure things that are much further away. All right, let's do some worked examples. I should have about 10 minutes left. Yep. Let's do some worked examples and then I'll be done with this video. Calculate in light years the length of 1 parsec. 1 year equals 3.154 times 10 to the 7 seconds. Okay, so the first thing we need to do is figure out, well, what is a light year? We already know what a parsec is. So parsec is 3.086 times 10 to the 16 meters. So what we'll do now is we'll calculate how far a light year is. And so the way you calculate a light year is it's the distance light travels in the time of 1 year. So we want to find distance, so S equals VT. And so the S is going to be 1 light year. So 1 light year is going to be equal to the velocity, which is the speed of light. So it's 299, 792, 458. If you know it, that's great. And the time was this time up here for 1 year, 3.154 times 10 to the 7 seconds. So this will tell us how far a light year is. You just take the speed of light times the number of seconds in a year. And you'll see that when you do this calculation, the seconds will cancel out, giving you just meters. So let's go ahead and throw that in the calculator. So I'm using the exact speed of light just because I want to show off that I have it memorized. 299, 792, 450. Also, that is the exact speed of light. Like it's not rounded off or we're not leaving off decimals. Like this is exactly how the speed of light is defined in physics. It's defined as this constant value. 3.154 times 10 to the 7. This number is rounded. All right, so I get this as being 1 light year. So 1 light year is equal to 9.455 times 10 to the 15 meters. So now what we want to do is we want to figure out, well, what's the length of a parsec in light years? So all we have to do for that is to just take a parsec per light year. So how many parsecs per light year? So we're going to set up a ratio that says 1 parsec. We'll set up a ratio in a second. First, I just want to write down this. 1 parsec is 3.086 times 10 to the 16. 3.086 times 10 to the 16 meters. That's 1 parsec. So now to set up a ratio, I'll divide both sides by a light year. So divide by 1 light year, and then divide this by 1 light year. 1 light year is 9.455. 9.455 times 10 to the 15 meters. Okay, and so you'll see that the meters will cancel out, and we just have to take that 3.086 times 10 to the 16 divided by that number we just calculated for the length of a light year, and then we get 3.26. So 1 parsec is 3.26 light years. That's a very useful.
4 sig figs, Keppel?
What's up?
Shouldn't it be 4 sig figs?
No, because the way it works is like when you do intermediate calculations, I'm carrying that extra digit there so I can justify that third digit down there. Because the numbers before were rounded off, I can only say it's 3.26. I can't get any precision on that fourth digit there. I'm not going to follow the sig fig rule, I guess. I feel like this is more valid. Like if you were to go ahead and calculate this out with the exact, so like up here, I don't remember if this number was exact or not, but if you went through and tried to carry it exactly, then you might find that 3 after the 6 might not actually be a 3. And so I don't know. I don't want to have rounding errors, so I'm just going to cut it off at 3.26. Okay, remember that conversion. It's gonna be useful. It's actually in the I think it's in the IB Physics data booklet. Okay, let's do 3 example problems. Number 5. Determine the distance to Procyon, which has a parallax of 0.285 arc seconds. So determine the distance to Procyon, which has a parallax of 0.285 arc seconds. Okay, so to find the distance, we're just going to take d equals 1 over p, and all you got to do is just take 1 over 0.285. That's it. And so if it's these problems can be really, really simple. So 1 divided by 0.285. And so I get this 3.5. So this star is 3.5 parsecs from the sun. Super simple. So remember, as long as you're putting it in arc seconds, you're going to get it out in parsecs. So that's the way that this works. If you put in an arc second angle, because of the way we set it up here, where we took an arc second, we calculated the radians and then plugged that in and got the parsec, that's how the parsec is defined, then this is always going to return parsecs when we plug in arc seconds. Let's do a slightly harder problem. The distance to Epsilon Eridani is 10.8 light years. Calculate its parallax. Okay, so the first thing is this is given to us in light years. So the very first thing we need to do is to convert this into parsecs. So here we go. So 10.8 light years. We want to convert it into parsecs. So we're going to say that 3.26 light years is 1 parsec. So now we just have to take that 10.8. And this is why we needed to remember that conversion, because it will come up from time to time. So 10.8 divided by 3.26. So I get it's 3.31. So 3.3. I'm going to carry an extra sig fig because I have 3 here. So that means I need an extra one here to be able to get 3 in my final answer. 3.31 to 3. What am I having problems with here? 3.313 parsecs. Okay, so now what we're doing is we're trying to find the parallax angle. And so just algebraically, you can see that you can just swap the d and the p. If you multiply both sides by p and divide both sides by d, then you get that the parallax angle is 1 over the distance measurement. So I'll just take 1 over 3.313, and then I'll have my parallax angle. So just take this and then raise it to the -1 power. So the parallax angle is going to be 0.302. 0.302 arc seconds. When you get really good at doing these problems, you can just look at the arc second angle and then like convert it over to a parsecs, like really quick. Okay, this is my last question. See how I'm doing on time. So I'm going to talk to you guys about using the Hubble Space Telescope to measure an object on the moon. So I also wanted to show you guys this picture. So I know we talked about the arc second, but the arc second is just so small that I have trouble explaining it. But this is an arc minute. So an arc minute, if you stood 780 meters away from a soccer ball, the soccer ball would appear to take up 1 arc second. And then you could go out to figure out 1 arc minute. Sorry, I think I said arc second. I meant to say 1 arc minute. An arc second would be you'd have to go super far away. That'd be a fun problem, is like calculate how far you need to be away from the soccer ball for it to be 1 arc second. And you would have to be further away than you could possibly be on Earth. It'd be something in space. Okay, I want to show you guys this is the Apollo 17 landing site on the moon. So when Apollo 17 went to the moon, you guys know we're going back to the moon, right? We're United States is going back to the moon, yeah?
I think I've heard about it a little bit.
Yeah, we are going back. We're working on it. It's exciting. But I was going to say, okay, so as part of the reconnaissance of like planning these next stages of the moon missions, well, we actually want to take the most powerful telescope in the world, the Hubble. It's not in the world, it's in space, but the most powerful telescope we currently have available to us, which is the Hubble Space Telescope, and we're going to actually use it to take photos of the moon. So here's an example of Hubble taking a picture. This one down here, this is the high resolution image of Hubble taking a picture of the Apollo 17 landing site. And so I mean, it's hard to tell, but I guess like you can see maybe these mountains in the background here, or like these guys here. I'm not really sure. I haven't studied this picture very long, but the point I'm trying to make is what's what's the resolution of this picture? Like how wide is that crater? You know, if we looked at this image, could we determine the resolution, like the scale to which Hubble could view things? And you just use the exact same equation that we've been using. So imagine that the way it's going to work this time is you're going to have this, you know, this angle here. So I'm already out of time. How did that happen? All right, so we're going to have, so we're going to have this angle here. Wait, what am I doing? Angle, that's not an angle. This is the angle. We're going to have this angle here. And then we're going to have, let's see. This is like the, what's that equation from math? Is like the sector arc, what's it called? Arc length. And then I'll call that D. Okay, it says the resolution of the Hubble Space Telescope is about 0.05 arc seconds. Estimate the diameter of the smallest object on the moon that can be resolved by the telescope. The Earth-Moon distance is 3.8 times 10 to the 8 meters. Okay, so what we're trying to figure out is, you know, if we want to know what is that distance there, if our telescope is capable of measuring down to angles that are 0.05 arc seconds, then what would be that? So the equation from math is that S is equal to theta times D. So if we want to figure out what S is, we just have to put the angle, and so that's the arc second angle. So that's 0.05 arc seconds. And then times the distance, which was 3.8 times 10 to the 8 meters. This isn't going to work though, because arc seconds needs to be radians. So we have to convert arc seconds into radians. And so we kind of did that up here, where we took the arc seconds and we converted into radians. And so we have to multiply that whole thing by this disgusting conversion factor here, which is going to be gross, but I'll do it. Let's see, can I use this result? I guess I could just use this result right here, right? That 1 arc second is 4.848 times 10 to the -6 radians. I think I'm going to cheat and just do that. So I can take this value here, whatever this is going to be, and I can multiply by that number that we just had up there. So 4.848 times 10 to the -6 radians per arc second. Kind of running out of space here. Let me see if I can move this over. There we go. And so now my arc seconds will cancel out. And then remember, radians they're unitless. There actually isn't unit there. So we just are going to get meters. So now all we have to do is just take these numbers and just multiply them all together. So here we go. So 0.05 times 3.8 times 10 to the 8. That's the distance to the moon. And then times 4.848 times 10 to the -6. Should be 100. Yep, there you go, 92. So S is 92 meters. So the Hubble Space Telescope can't detect anything, or won't be able to make out anything less than about 92 meters across. So if you had like a, you know, the rover that the astronauts were on, that's the wrong one. The rover that the astronauts were on, that's way less than 92 meters, and so that's why it's not going to show up on this image, even though we left a bunch of stuff there on the moon. The Hubble Space Telescope won't be able to pick it up because it's too small for the telescope to be able to detect. It's not sensitive enough to see it. Okay, that's it. I'm done. I'll see you guys later. I'm going to leave this last problem here on the Gaia Space Telescope for you to complete on your own to demonstrate to me that you understand how to do this. Have a wonderful day. I'll see you later.